Welcome to my YouTube channel. In this video lecture, I am going to answer the next 10 questions from Airborne Weather Radar chapter Heat Variance. Previously, I have solved first 40 questions. In this video lecture, I will be solving the next 10 questions, question 41 to question 50. So let's start with question 41. On a color airborne weather radar, that means airborne weather radar which is using colors to depict information or to depict different kinds of returns. A bright red echo determines or indicates what? So remember that there are four colors. The black color is used to indicate very light or no return. After that, green color is used to indicate light returns. After that, yellow color is used to indicate medium return. And the last, red color, is used to indicate heavy returns. Heavy return. Now this returns that we are talking about, this returns are nothing but reflections from large water droplets. From large water droplets. Okay, remember this. So very light or no return means very light return or very light reflection from a very few water droplets in the cloud. Light return means a little bit more than the previous very light return. Medium returns, that means you are getting reflections from uh, a good number of water droplets in the cloud. Heavy returns, that means that cloud is concentrated with dense large water droplets. Okay, so the correct answer here will be heavy concentrations of liquid water, okay, rain and solid water. It can be ice crystals, hail, like that. So the correct answer here is option delta. Now option Bravo, area of extreme turbulence. Yes, that is also right. That a red color echo or red color is an indication of the presence of huge concentration of water droplets in the cloud. Now wherever there are huge concentrations of water droplets in the cloud, so you can expect turbulence. But mainly, in case of airborne weather radar, you always remember that turbulence is indicated when different colors like red, yellow, green, different colors are close together. Different color zones are close together. Okay, so that transitional zone among different colors is where you are going to expect heavy turbulence. It's not necessary that just because there are red echoes on your screen, in that red color zones you will expect turbulence. You will expect even more turbulence in areas or zones where there are different colors. Okay, that means the transition from a green color, that is a safe area, to a yellow color where there is medium reflections, to a red color area where there are heavy reflections. Okay, so when all these three colors are combined, okay, are in adjacent to one another, you are going to expect turbulence as you transition from one zone to another zone. So that is the right answer. So extreme turbulence is where different colors are close together. 42. ISO echo feature of an airborne weather radar can be used to detect what? Now, just like this, now this is one form of display in which we are going to use colors to represent information. There is another kind of display called monochrome display. Monochrome display, also known as black and white display. Black and white display. So in this case, the information will be represented by black and white colors. Now here, over here, white color means presence of turbulence in the cloud. Turbulence in the cloud. Okay. So it will be surrounded by black color boundary like this. Now this black color boundary is nothing but your cloud. Okay, and the white color inside that boundary is where you're going to get your expect turbulence in the cloud. So remember, ISO-echo feature of an airborne weather radar can be used to detect wake turbulence. No. Turbulence in cloud. Yes. Areas of possible turbulence in cloud. Uh, Clear air turbulence. So correct answer is option Bravo. Turbulence in cloud. 43. On the airborne weather radar display, the most severe turbulence will be shown by steep color gradients. Yes, like I said, it will be shown by the presence of different color zones close together, close to one another. So for example, red color zone, yellow color zone like this, and green color zone. Okay, so these different colors are very close together. So just like a front, in meteorology, we have studied about fronts, a boundary between two contrasting air masses. Now, when you transition from a cold air mass to a warm air mass, across that boundary, you're going to expect wind shear turbulence. So just let's say, similarly in this case, when you transition or when you fly across from one green color zone to the next yellow color zone to the next red color zone, you as you transition across different zones, you're going to experience turbulence. So steep color gradients. So steep color gradients means what is gradient? Gradient is nothing but a change in some factor across a distance. Now, when these color zones are very close together, that means these colors there is a change in color, change in one color factor across a very short distance. So that means you're going to expect turbulence. Okay, very dangerous turbulence. Steep. That's why we call it steep gradient. That means the change in the precipitation, intensity of precipitation across these color zones is very steep. Okay, is very severe. So flashing red is wrong. Black hole is wrong. Alternating red and white stripes, again irrelevant. So option A is the correct option. 44. Airborne weather radar uses a particularly high frequency radar band 9 to 12 GHz in order to get good returns from droplets of water and other sorts of precipitation, get most accurate range and bearing information, make it possible to present a color display. All of the answers in the questions are correct. So the correct option here is option alpha. Get good returns. Now, the frequency band in which airborne weather radar operates, 9 to 12 GHz, has a corresponding wavelength in terms of centimeter, 3 centimeter, 30 millimeters, okay, in terms of centimeter. So what happens that we are concerned about large, large water droplets. Airborne weather radar tries to obtain reflections or returns from large water droplets because this large water droplets is where the because this large water droplets will be found in cumulus clouds, cumulonimbus clouds. Contrary to this, small water droplets will be found in clouds which are not dangerous for aviation safety. So we are only concerned about large water droplets, and these large water droplets are tend to be 3 centimeter, okay, around 3 centimeter. And therefore, when we use this particular wavelength from 9 to 12 gigahertz, the wavelength of the radar signal is somewhere around 3 centimeter. Now, when the wavelength of your radar signal is equal to, okay, is equal to approximately the size of water droplet in the cloud, the radar radio signal will get reflected. If the size of the water droplets is very less than the wavelength of the radio signal, then this radio signal will penetrate the cloud and go through it beyond it. Okay, will penetrate the cloud and go beyond that cloud. So in order to get reflections, the size of the water droplet must be equal to the wavelength or somewhere equal to the wavelength of the radio signal. And it is found that large water droplets tend to be of 3 centimeter diameter, something like that. So the wavelengths that we need should be also equal to that value, and therefore we use frequencies in the band of 9 to 12 gigahertz, because in that band you are going to get a proper balance of wavelength, okay, a wavelength and good reflections. So that's why we use 9 to 12 gigahertz. So I'm going to write here, when size of water droplets equals the wavelength radar pulses, the radar pulses will be, or the radar pulses will get reflected when the size of water droplets is much less than wavelength. The radar signal or the radar pulse will penetrate the cloud and go beyond it, and go beyond it. Okay, next. 45. Airborne Weather Radar unit transmits a 5-degree beam width of 5 degrees from a parabolic dish aerial reflector. If the wavelength is 4 centimeter, what is the diameter of the dish? Now you have to use a direct formula which says beam width equals to 7 into wavelength divided by antenna diameter. Let's substitute the values. Beam width is 5 degree, wavelength is 4 centimeter, so diameter will be 28 by 5, which is 5.6 centimeter, not 7. 70 into wavelength, the formula is 70 into wavelength divided by diameter. So 70 into 4 divided by 5 is 56. 56 centimeter. Okay. So 5. So here the options are wrong, but the answer is right. It should be 56 centimeter. Next, 46. Again, 4 degree beam width wavelength 3 centimeter, what is diameter? So beam width is equal to 70 into wavelength divided by diameter. So diameter will be equal to 70 into 3 divided by 4. So 70 into 3 is 210 divided by 4, that is 52.5 centimeter. Option delta. 47. Beam width is given 4 degrees. At what maximum range will it be able to detect 1 nautical mile wide opening in a sea cliff? So that means there is aircraft here. There is a sea cliff, means there is an opening between these two cliffs, and that opening is 1 nautical mile. We have to calculate the horizontal range. Beam width is 4 degrees. Degree up, 2 degree down. So we have to calculate this horizontal distance from aircraft, okay, to the cliff. So this one nautical mile can be divided into two parts. So I am drawing this triangle again. We are only going to consider the upper triangle. So this is 2. This is what we have to find out, x. This will be 0.5. One will be divided into two parts. 0.5 for this triangle, another 0.5 for the triangle at the bottom. Okay, next. So let's use 1 in 60 rule now. 1 in 60 rule. Angle equals to distance of track divided by distance gone to 60. So angle of track is 2 degree, right? Distance of track is 0.5. Distance gone is x into 60. So x equals to 60 divided by 4, which is 50. So 15 nautical mile is the answer. Option brown. Next. 48. The tilt on the airborne weather radar at which an active cloud just disappears from the screen is 4 degrees up. If the beam width is 5 degrees and the range to the cloud is 40 miles, using 1 in 60 rule, calculate the approximate height of the cloud relative to aircraft. So, height of the cloud is equal to tilt minus beam width by 2 into range into 100. Tilt is 4 degrees up, beam width is 5 degrees, range is 40 into 100. So 4 minus 2.5 into 4000. So that is 1.5 into 4000. So 1.5 into 4000 is 6000. So the cloud is 6000 feet above me. Okay. Plus the answer here is plus 6000. So answer will be 6000 feet above you. And also you can see the tilt is 4 degrees up. Tilt is 4 degree up. That means the cloud, this layer of cloud will be above you. Next, 49. Aircraft is at 25,000 feet. The beam width is 5 degrees. Radar tilt is 3.5 degree up. The radar is showing top of a cloud return at 105 nautical miles. What is the height of the cloud? So again, the height of the cloud will be equal to tilt minus beam width divided by 2 into range into 100. So tilt is 3.5 degrees up. Tilt is 3.5 degrees up. Beam width is 5 degrees. Range is 105 into 100. So 3.5 minus 2.5 into 10500. So that is equal to 10,500 feet. Okay. So aircraft is flying at 25,500 feet. So let's draw aircraft. This is where your aircraft is. This is the horizontal datum. Now the distance between your aircraft and this datum is 25,000. There is a cloud layer which is 10,500 feet above you. Okay. So this is 10,500. So height of the cloud is total height of the cloud will be equal to 10,500 plus 25,000, which is 35,500. Correct option is option delta. 50. Beam width is given to you, okay, of 5 degrees. Now how will you orient it to receive returns from clouds that are at or below your level? 2.5 degrees down tilt, 2.5 degrees up tilt, to 5 degrees down tilt, 0 degrees tilt. So you want to receive returns from clouds that are at your level or below your level. So what you will do is, now let's say there is a cloud, this is your aircraft. Beam width of that aircraft is 5 degrees. That means, let's say this is your horizontal datum. The beam width is 5 degrees, so 2.5 degree up, 2.5 degree down. Now you want to detect a cloud which is below your aircraft level, which is below your aircraft level. So here is your aircraft. There is a horizontal datum just like before. Now, since the cloud is below your aircraft level, below your aircraft height, you will have to tilt this radar beam downwards. That means this top part of the radar beam will get aligned with this horizontal datum, somewhat like this. Okay, so 2.5 degrees, 2.5 degrees. Okay, so this bottom part will be this, and this top part is this, which is aligned with the horizontal datum. So if there is any cloud which is below your level or at your level, it can get detected by this when you tilt the bill 2.5 degrees down. So the correct answer is 2.5 degrees down tilt, option A. Okay. So this concludes our lecture. I hope you have understood all the 10 questions I have solved, explained, answered. If you have any doubts, comments, feedback, let me know in the comment box of this video lecture. I wish you all the best. Subscribe to this channel, share this video with your friends, and don't forget to hit the like button. In the next video lecture, I will be solving the next 10 questions. So do watch that video lecture as well. See you.